So component form is that A, B form with your arrow brackets on either side. So that just tells you to find A, which is our magnitude times cosine of a directional angle. And a B is our 18 times our sine of 347, which came out to 17.5, negative 4. Be careful on this question because I could ask what is the magnitude? The magnitude of your components. If I asked for the magnitude of the components, your answer would be 17.5 and a positive 4. Magnitude always tells you to find the absolute value. This one just asked for component, didn't ask for magnitude, so then you knew your answer had to be in that form. All right, questions on that? Okay, questions from the homework. Yeah. Specific question. Oh, it's smaller than 12. Did you find 13.1 for your resultant? It should have came out as 13.1, so that's probably where the mistake happened. Let's look at mine really quick. So you should have this drawing where you had 12 and 2 on your sides, or it could have been 2 and 12, however you had it drawn. And then to find v, you would have had v squared equals the two sides, so 12 squared plus 2 squared minus 2 times 12 times 2 times cosine of 120, because that is the side opposite my result. Okay, you had all this correct? Okay, then yeah, I'm sure it was just a calculation error between all of those. But usually if you got one of those wrong, it's probably because your resultant got wrong somewhere. It's a lot of stuff to plug in a calculator all at once. Are you okay with that then?
Yes.
Okay.
Wait, can you keep that up for like 2 seconds?
Yeah, it's also online.
Okay. Yeah, I know.
It's available 24/7 to you. 365. Well, you have your phone. That's true.
And I don't even have a phone.
All right, today we're going to talk about complex numbers in the complex plane. Right? I said,
I is negative square root of 1. Right?
yes, it is. It's an imaginary number, which is the square root of negative 1. As we're doing this, do not overthink it. This is almost the exact same. Today is going to be almost the exact same as what we did with vectors. It'll be almost exactly the same. We're going to make little alterations at the end, but the bulk of this is going to be the exact same. So complex numbers on the complex plane. Complex numbers come in this form, and it is a plus b times I, where a is called our real component, so let's call that's our real portion of it, and b is our imaginary. So we have a real component, and we have an imaginary component, and then we have an I tacked on the end. But since every imaginary number comes in this form, we can rewrite this on the imaginary plane as the point A, comma, B, where A is my real portion, and B is my imaginary portion. So it looks a lot like an x, y coordinate, and in fact it is. We just have to rename this to no longer be x and y, but instead my x-axis is going to become my real axis. We'll just call it my real. And then our y is going to become our imaginary axis. Which is weird, because one doesn't exist. So we have an imaginary and a real axis when we're talking about imaginary numbers. Now we're going to plot it just like I would any old point. That is just A, B. Well, let's get some points we can actually plot on this. So I forgot what example I was going to do. So we're going to graph these on the coordinate system. So the first one we're going to graph is 2 plus 4i. 2 is my real, So 2 would go on my real axis and 4 would go on my imaginary axis. In other words, if it makes it easier for you, you could change this to the point 2, comma, 4. And then we just go to our real imaginary axis here and plot the point 2, 4, which is about here. So that point right there is the point 2, 4, or we can call it the 2 plus 4i. Now here's where imaginary numbers and vectors start sharing a lot. It is not just that point. It is actually this line. We could think about imaginary numbers as having that line. And that line has a distance. In vectors, we called it our magnitude. Our magnitude, our V with our big absolute value signs around it, right? Magnitude comes with absolute value signs. With imaginary numbers, we actually call it our absolute value. But it is no different than our magnitude. It is the same thing. So absolute value is our magnitude. It's just we give it a different name so we know we're talking about complex numbers. So anytime I say absolute value when we're talking in this section, just think magnitude. In fact, it's going to have the exact... Did someone die? It's going to have the exact same formula attached to it, and we'll see that down below. All right, the other thing, we're going to do one more example, just because it's one of those weird ones. Maybe we'll do 2 more. Let's say I have 2i. What point would 2i be? Yeah. It would be 0, 2, because I could rewrite 2i as 0 plus 2i, which would be 0, 2. On our axis, that point would be right here. Ah, my snap grid. It's not letting me go to the word. Close enough. Close enough. So that is my point, either 0, 2, or it's just 2. All right, let's try one more. Let's do -2. I want to plot -2 on my imaginary grid here. What would that point be, Nick?
-2 plus 0i.
It'd be -2 plus 0i, so it'd just be the point -2, 0, because I don't have an imaginary component. That'd be -2, 0.
So that's a completely normal number.
It is a completely normal number. Completely on my real axis. It doesn't even dip in the imaginary world, which is above and below it.
So sad it can only be like on that line or else it's not even
Otherwise,
real.
it's partially
Yeah.
imaginary. Yeah. All right. Treat complex numbers like vectors. One more time, I want to put this down here. Absolute value equals magnitude. And we're going to do that for this section right here. So we're going to walk through some things, and also we'll realize, hey, it's exactly the same thing as vector. We didn't have to walk through it, but I want to go through it again. All right, absolute value is distance, just like magnitude is distance. So let's look at that first example. The first example says plot 3 plus 4i. Well, I already did that for you. And then it's basically is find the absolute value. Remember when you're plotting these, if you ever get confused, just make the point 3, 4. So we're going to go ahead and find the absolute value of this. Absolute value, which is just the distance. It's just the distance from here to here. But like vectors, just like vectors, we create a right triangle. That is not anywhere near where I want to go. So we're going to create a right triangle, where the base of that triangle is 3, and the height is 4. With vectors, a lot of times, or with imaginary numbers, we're going to call our absolute value r, or that length r. Now, if I told you to solve for that, I just gave you that triangle, you'd probably reach back to geometry and say a squared plus b squared equals c squared, right? So in
Not right though.
it is right.
Thank God. I was gonna say if
Yeah, I thought for sure you were gonna have it under some crazy method. Yeah.
So we could say r squared equals side squared, or 3 squared, plus 4 squared. But if I was solving for r, I would just say r equals the square root of 3 squared a squared plus 4 squared b squared. It's the exact same formula as your magnitude, because magnitude was the square root of a squared plus b squared. Our absolute value is the square root of a squared plus b squared. It is the exact same. So if you see absolute value, think magnitude. It's the same exact formula. So for this one, it's going to be 3 squared is 9, 4 squared is 16, 16 plus 9 is 25, the square root of 25 is 5. So I'm going to write that down there, just that little formula. R equals the square root of a squared plus b squared. It's important to know that for your absolute value. But of course, it's not too hard to remember if you remember magnitude, because it's the same thing. Go ahead and do the next one. Find the absolute value of the next one. Of 5. And I want everyone to look at the answer, because notice this is another way to put this. It doesn't have to be just r equals. You can say, well, the absolute value of what I'm given equals that, because it actually is the absolute value of this. So absolute value sign is the exact same thing as our r equals that. But absolute value of this, magnitude of this, length of this, however you want to think of it, is square root of 5, because it's the square root of a squared plus b squared. Does that make sense? If you're good on magnitudes, you should be good on this. If you weren't secure on your magnitudes, then this is probably tricky. The next part, if you just avoid this little section here for right now, is stuff we already did with vectors as well. Whenever we had a vector, we created a right triangle, we could find information from that right triangle. Specifically, if I have a right triangle, you can automatically think cosine, sine, tangent, that sort of thing. So we're going to start out with cosine on this guy. We're going to start with cosine on this guy, and we're going to say cosine of theta. Cosine, so cosine is adjacent over hypotenuse, so that's A over R, but I could rewrite that as A equals R times cosine of theta. Did we ever see that formula before in our lives? Yeah, Luke?
It's r times cosine of theta
Equals WX or A. Yep. It's just our horizontal movement. So we have this exact same formula with vectors to get my A value. In fact, we just did that for bell work. We did this exact same formula for bell work. So guess what we're going to do in the next one? We're going to find the sine of theta. So sine of theta equals B over R. Well, that just gives me B equals R times sine of theta, and we learned nothing new. We've been, right? Yeah. We've been in here for like 10 minutes talking about nothing new for a while, just applying it to our trig form. If you look down below, it says if z equals a plus bi is a complex number, then the trig form of that would be r times cosine theta plus I times sine theta. All that comes from This whole thing comes from the fact that A plus BI equals, if I substitute A in for it, we're going to get R cosine theta plus R sine theta times I. And all I'm saying is you can factor out an R to get this equation. All right, but all I am is replacing my A's and B's with these values. That's all this is saying.
A's and B's with these.
A's and B's with these. All right, something a little more new is just some terminology. Our R, which is our kind of our length. Oh, oof, that's terrible. R is our. R is our. It's our length. It is our absolute value in the book, and sometimes it is called our modulus.
Sounds like a disease. So you have modulus. You have two.
It is called a modulus. I want to make sure I spelled it correct. And sometimes our theta, where it was our directional angle, and I'll still probably call it our directional angle, honestly, is sometimes called the argument.
Well, that's just.
Well, it's better than a terminal disease.
That's true.
Why are we thetaing like this?
All right, so if R is called the modulus, theta is called the argument. At no point are you 100% required to do this. I will not on the test say find your argument and find your modulus. You will know what you're looking for. Okay? But this isn't new. You should know how to do this. So let's apply what we just did. So this one says write each complex number in trig form. Trig form is this form. Is our A and B replaced with our R times cosine theta and our R times sine theta. So that means I need to find my R and I need to find my theta. Well, I'm going to go ahead and find the theta first because we've been finding thetas forever and I want to start with that. So if I want to find my theta, I'm going to first find my alpha because my alpha is right there. Let's write it in there. That's my alpha. This is the triangle I formed that has a height of 2. Negative 2 square root of 3 on the bottom. So I'm going to go ahead and say the tangent of that there alpha is going to equal the opposite, which is 2, over negative 2 square root of 3. We should know by now that it means I'm going to take the tan inverse of both sides. Unless I'm wrong, equals 30 degrees. Now be careful about entering this in your calculator because you're going to probably get out 60 the very first time you do it. And that is because in your calculator... No, we want degrees. It was a good thought. In your calculator, most of you are going to fall in the trap of typing in tan inverse. And then you'll type a 2, a division sign, a negative 2, a square root of 3, and close your parentheses. That will not get your right answer because in your calculator, if you kind of think about how that's going to be lined up, it's going to do your 2 divided by negative 2 first, and then it's going to multiply it by square root of 3. This negative 2 and square root of 3 need to be in parentheses all by themselves. Like I said, I always fall in the category of I use too many parentheses when I use my calculator. I'll put my numerator always in parentheses, and I'll always put my denominator all the way in parentheses, whether I need to or not. But that should come out to 30 degrees, and not just 30 degrees, it should come out to negative 30 degrees. And you should have known that already because your theta has to be 180 minus something. So our theta is going to be 180 minus 30, which equals 150 degrees. All right, that's my theta. That's my theta. The next thing I need to find is my R value. My R value or my absolute value or my magnitude, however you want to think about it. Well, that's just going to be R equals the square root of our A value, which is negative 2 square root of 3. Square that baby, plus our B, which is 2. You know that's getting squared. which is going to give us the square root of, so negative 2 squared is 4, square root of 3 is 3, so it's 4 times 3, which is going to give me 12, plus 4, which equals the square root of 16, which equals 4. My r value is 4. And now it just takes knowing that trig form is r times cosine theta plus I times sine theta. So that's going to give me 4 times cosine of that 150 plus I times sine of that 150. Got it? Love it? Meh. Well, guess what? You're doing the next one. Whether you like it or got it, you're going to try the next one. All right, so this is our answer. Hopefully you got it or you know where you made your mistake. All right, last two things. They're pretty easy. These are pretty easy. It is going the opposite way. It was what Nick was trying to do to the next one and simplify it further. It's kind of like taking this and putting it into our a plus bi form. In order to do that, there's two different ways. I do not care which way you do it. I kind of alternated between in the solution key how to do it. I typically stick with the second one, and I'll tell you why, but we'll go through two different ways to do this. The first way is either look at your unit circle, because it could be on your unit circle, because cosine of pi over 4 is, or you might have to plug it in your calculator. But in this method, what we're going to do is we're going to replace our cosine pi over 4 with what it actually equals in degrees, or radians, I mean, doing our xy values. So we'll have square root of 2 times the cosine of pi over 4 is actually square root of 2 over 2 if we look at our unit circle. Plus our I times, so that's my cosine pi over 4. Sine of pi over 4 is also equal to square root of 2 over 2. Well, that's nice. Then you just have to distribute, maybe I should do it underneath. I don't have room. I'm going to distribute that square root of 2 to both of these. So that's going to give me square root of 2 times square root of 2 over 2 plus I times square root of 2 times square root of 2 over 2, which is going to equal 2, square root of 2 times square root of 2 is 2. 2 divided by 2 is 1. Plus, and that's going to be 1 also. I'm going to put the 1 in front of the I, or we could just leave it off and say it's 1 plus I.
That's what I did.
I typically leave it off because it's kind of like if you talk about 1x all the time and 1y, it kind of gets annoying. What's your 1x and 1y value? You mean your xy value? Questions on that method? Not bad, is it? The other method is this. Or you can just remember the fact that A equals your absolute value or your magnitude times cosine of your theta, which is 143. Let's leave it as theta for right now because we're just using letters, which is going to be the same thing as 3.6 times the cosine of 143 degrees. And that's just going to go ahead and equal about negative 2.9. Our b value is going to equal r times sine of theta, which in this example is going to be 3.6 times sine of 143 degrees. That turns out to be about 2.2. Now our rectangular form is a plus bi, so we just take our a value. Let's put that down. A plus bi is going to equal, replace the a with negative 2.9 plus our b, which is 2.2, and attach the I onto it, and that is your answer. I do not care which method you use. I typically go to this one because I can plug all of this in and get a number. I can plug all of this in and get a number. Here you kind of plug this in your calculator or go to unit circle and do it down here, and then you do another multiplication. So this is sometimes nice because it's all in one row. But this is sometimes nice because it stays in the correct form. You're not breaking it apart into A and B and trying to put it back together. So I really do not care which method you do. Make sure you do one of them, because it is the only way to get your answer. All right, any questions, comments, concerns of what we covered today? Yes?
Is he gonna get to a point